All right, welcome to Research Jam 24. This will be the last one of this year. For those who are attending or participating for the first time, this is the equivalent of a lab meeting as in a traditional lab where lab mates show up and show what they've been working on, small progress, mostly research in progress. So very, very rarely you'll see research that's already published. So that would qualify an entire talk. But here we have small updates. And for us is a way to sample the community and see what people are working on these days. And today we have a pretty fun combination of different topics. Neurocellular by Meet, that's gonna go first. And then we have an RFP, a tensor visualization library, and a supervised contrastive learning coming next. So Meet, you can go first if you're ready.
Sure. Okay. So just a little bit about me. So I'm talking about this meta neural cellular automata work that I'm working on. I run this company called Mythos Scientific, where it's just me. I'm doing consulting for different companies in like the AI space, and then I do this independent research myself, where I'm interested in like meta learning and kind of new ways to train neural networks. So just to start quickly, the motivation for this work is to try to fix some of these disadvantages of traditional neural network training. It's like it's a pretty preliminary project, so it's just like one step in like several steps that I would see in order to do this. But so the first problem is that these gradient calculations for traditional neural network training is pretty expensive. And once they're trained, these neural networks are not really easily able to learn online or at test time. I mean, we were talking about this test time training thing just a little while ago, but yeah. So in like real biological neurons, where it's probably not what the biological neurons do. That is backpropagation and gradient descent. So they're mainly governed by like local interactions where neurons communicate with each other, and you have this collective behavior of the system that allows it to learn altogether. And given those differences, the biological neurons use way less energy and are much more sample efficient than our traditional neural networks that we train. And they also learn continuously and robustly and these types of things. Very different from traditional neural networks as we have them. So my thought in general is that what if we had these local interactions as the way that neural networks learn instead of a global update of gradient descent? And from these local interactions, we have this whole system that self-organizes into a state that performs well on that task. And given this much more efficient way of getting to that end state, we would be able to much more quickly sample weights for many different architectures for a single task, because it has weight level parallelism. And if you guys have any questions, you can stop me for sure. I don't mind. So just to talk about the words in my title, meta neural cellular automata. The first thing is the cellular automata here. So if you're unfamiliar with Conway's game of life, it's an example of cellular automata where you have a system where you have a grid of cells and you have two states, either dead or alive. And depending on the number of alive neighbors, a cell is born, dies, or stays alive, or stays dead. And just from the simple, this kind of simple neighbor rule, you have very complex behavior. This is just like one of the kinds of configurations that you can create based on some particular starting conditions. So it's a really well-studied system in computer science, and people are still continually making discoveries of new behavior that this system does. So from the simplest rules, we have like complex behavior emerging, and that from that kind of inspiration I take for these things for creating a new system that learns. So there has been other work using cellular automata as a basis for machine learning purposes. There's this work which I can show right now from these. So this is a similar kind of grid system which produces an image in this case that is governed entirely by local rules. And so instead of the simple neighborhood counting, you have a neural network itself being used as the local update rule. So it takes into account the neighboring pixels, as well as hidden state vectors that every pixel in the grid has. And so based on the neural network that is used as this local update rule, the current pixel value changes. And so this kind of system, they train the local rule in such that this particular emoji is the attractor state of the system. So you have this, at first, this is not what is created by the local rule, and then based on many applications of this local rule network, you calculate the differences between the pixel values of the real emoji and what you have at the end of the applications of the local rule, and you train that local rule based on that loss. So this exhibits a lot of properties just on its own that are like regenerative, and this type of behavior you don't really get from like a lot of image generation algorithms. So I think it's an interesting system. But so now in this project that I'm doing, I'm basically trying to apply this neural cellular automata idea, but instead of running it on an image or anything else, I have two neural networks. I have the task neural network, which may be like an MNIST classifier, and the weights of that neural network we can think of as the cells on a grid. And we have a local rule neural network that is updating the weights of this task neural network. And so the local rule neural network is trained via gradient descent based on the task neural network loss function over several updates that the local rule neural network does to the task neural network. And so once the local rule network is trained, it's able to generate weights for any architecture to do that particular task. So how like the main.
Can I ask a question
Sure.
here? So I'm not exactly sure which parts of the problem you've like restricted versus not, but maybe it's worth thinking about. Could the local rule neural network learn actual SGD here? I'm guessing the answer is no, because it doesn't have access to a backpropagated gradient. Is that the only thing that's missing?
So I mean, what you could like, if you did allow it to, like if you fed that as input to the local rule network, like the gradient at any particular point, well, I mean, then you're already basically, you already did most of the computation that would be needed for gradient descent, I guess, anyway. So that wouldn't really give you any speed up, I guess, right? But oh, I guess you're saying for like the output. Like
I'm not imagining it would be somehow magically faster. I'm just wondering whether it's even possible for this to learn traditional gradient descent.
Yeah. I think
Gradient descent
so.
it is a local computation. It just requires kind of passing the gradient backwards one layer at a time, which is
So it's not parallelizable through the entire network at once. Like you
right.
have to do it one step at a time there.
Okay.
But yeah, I think actually, so if you allow like in the meta training phase access to the gradient for every parameter, you could train the local rule network to just calculate the gradient. But yeah, I mean, that's not exactly what I'm doing here, but I am still using the gradient in order to train the local rule network in order to optimize the loss. So it is, it could be doing that. I wouldn't say that it's impossible. Yeah.
What information then does the local rule network have access to? I guess that's the important question.
Yeah, that's so what all the local rule network does, right, is I don't know if you can see my mouse, but yeah, okay. So for a given weight, so it's only looking at one particular weight at a time. It has the weight itself, and each weight has a hidden state vector, and just like in the the image example from from 2020, this weight and a hidden state vector for every parameter. So the neighborhood of this weight, there's directionality to this. So I group all the neighbors of the previous neuron and the next neuron as the forward and backward neighbors of this particular weight. And so the local rule network takes these as all these things as input, but the neighborhoods, because they're of different sizes, you have to aggregate them somehow. So there's different ways of aggregation. You could do like a simple mean or some other kind of attention-based aggregation, which I've tried. So yeah, the local rule network has these inputs. It's just those inputs, and it doesn't have actual access to, like, an important thing here. It doesn't have actual access to the activations or like a loss signal itself. So it's not like at test time, at after the meta training phase, you don't, like, it's not able to like on the fly adapt to a new task or something like that. It will only ever, like, once the local rule is trained, it will only adjust the weights of whatever architecture you give it to like a particular task, like for that particular data set that you use to do the meta training.
So
we can get into, yeah.
So you give the weights as input and then it predicts the next weight, following weight.
Yeah, it gives you like the update to that weight. And based on, like, there's no right answer given to it. It just is optimizing the loss at the end. So it'll do these updates for like X number of like update iterations, and then at the end you calculate the loss of the task neural network with respect to all of the updates that this local rule network did on the task network. And then you optimize the parameters of the local rule network in order to minimize that loss.
So this, I feel like this is, have you seen like hyper networks by any
Yes,
chance?
yeah. It's I would consider this a kind of hyper network, except it's not adapting to new tasks or anything
Okay.
for now. Yes.
We have about a minute left. We should.
Yeah. So I didn't show you any results from this whole thing. It's kind of long to explain, I feel. So sorry about that. But this is like a very tiny example of this kind of system where every weight is being, all the weights are being updated as like in real time, and I'm like zeroing out like with my like the weights in red are being zeroed out, and it's growing back the weights in order for the accuracy to be on the iris task to be high. And then I have these, so like one of the ways that I test performance on these tasks is just like, okay, I include some architectures in the meta training phase, and then I have some architectures that are like different interpolations or like other architectures, and I apply the local rule on those other architectures that were not included in the meta training phase. And all of these are like validation set performances. So these this shows that like it doesn't have to be any, like the performances are still similar for things that were not, for architectures that were not included in the meta training phase, and this is for MNIST. And this is another kind of evaluation I did for like robustness, to like zeroing out the weights of like a particular layer, or like a random layer and like a percentage of the rest of the network, just completely zero out a bunch of weights, and then see if applying the local rule recovers the performance and how well it does. So it does, but it like degrades over time, and this kind of thing. What I would like to do is to scale this up and then try to test on like a less of a toy problem, and expand. I've already expanded it to like CNN architectures instead of just like feed forward architectures, and I want to try to do some like growing and pruning neurons during the local rules updates to see whether it can handle that. Because that's one thing that you can't really do with regular neural network training. So if you can do it with this, then that would be interesting. And yeah, I mean, this is, yeah, basically I want to include activations and loss signals later on for like real meta learning, for like actual task generalization. But for now, I wanted to prove this concept out of like doing any kind of updates with a local rule. So that's all I had to say, mainly.
Cool. Thanks for presenting. This is a pretty interesting direction. We should move to the next speaker just for time. We're a little bit over. Maybe if anyone has questions for me, feel free to put them in the chat.
All right. So my idea is somewhat of an extension to what Meet proposed and then what we discussed as time compute. So the idea I wanted to explore was language model swarm. Like I suppose everyone is aware of what swarms are. So one example of a swarm that we see here is like birds have a swarm behavior. They collectively go. And generally swarms have like they display this global behavior, and they are in large collections. And for example, in this case, these birds, right, they have like simple rules. I wouldn't suppose simple, but like they have rules that are like around the local neighborhood. Like they just mind about what they see next to each other, but they somehow collectively have this sort of like global emerging behavior. We see this in ant colonies as well. That's in the cellular automata Meet was saying, that's also another example. So, and the question a lot of people have been asking is like, okay, let's say if we set a global behavior that we want, and then and what kind of a local rules that will cause this local global behavior. And the same thing, it's I'm very surprised we had. It's very interesting. And this has been actually explored in 90s, especially in the amorphous computing research around that time, and they have tried a number of directions. And so the key idea I wanted to explore was, can we do something like a swarm behavior with LLMs? So in robotics, people have been exploring swarms. I think I've seen some groups but they're particularly they're very interested in sort of uh, algorithms that they can open up and then see. They haven't really explored like a black box models like LLMs. They want to see they have been solely focused on tractable solutions. So, and the question I have is what happens if we just use LLMs? Because I feel now that we have these reasoning abilities in LLMs, I was very curious. So, and the key couple of questions I'm interested in are so if we replace, for example, birds here with LLMs, can we somehow get these LLMs to form shapes? And each of these LLMs would have sort of a very simple rules that they can coordinate with the neighbors. And they can do the form motion. And then the other behavior that I'd be interested in is would they adapt to environmental changes? Okay, let's say there is one LLM that is down, or there are 10 of them that are down. So what would happen? Would they still reconfigure to kind of do this global behavior? So, and I was interested in can we just do this without sort of a training? Can we just use prompts and then somehow get them to kind of do this job? So there are a bunch of works the first two papers that I cited here were in late 90s. Those were the papers so they were applying this point cloud on 2D space. And in robotics community, they have been trying this to get actual hardware to kind of do this. Yeah, so this idea has been there with me for a while on my mind. But then the test and compute papers that I've seen recently that kind of got me back into this. For example, I'll show you a couple of papers. How do I stop this? All right. So there is this one paper I came across a while ago. This was in Nature Digital Medicine, evaluating multimodal AI with medical diagnostics. What they were doing was they collected a lot of radiology task data over 10 years. And they had about 945 questions, and then there were 90 people who kind of answered this question. I think this was somewhat crowdsourced. And then for each question, right, on average, they got about 49% of them were correct. But the interesting result in this paper was that they did majority voting on all the 90,000 responses that they got, and their majority vote was had a 90% accuracy, meaning all of these are relatively weak learners, in some sense. And then somehow, given this large number, and the result was so good. And I was thinking oh well, what would happen if we just take 100,000 of weak LLMs in some sense and then do this? And then the author actually pointed me to another paper DeepMind guys published. This is sort of a similar paper, similar idea, but they tried with LLMs, and then they tried with 256 LLMs, and then they were seeing whether we can get better results, and they surely did. For example, they were able to double or triple the performance, kind of doing some kind of and smart and summable, trying to find smart hyperparameters at inference time. So, and then the question I was asking was, well, what would happen if we have this swarm of such LLMs instead of like 100 or 200, like just scale this to like 100,000 or 50,000. I'm just speculating here, but like, can we kind of get these LLMs to do interesting tasks, especially like shape formation? And in robotics community, we are, for example, we are interested in like getting robotic hands to do interesting things. But for example, let's say if you have like 10 robotic hands or 50 robotic hands or in of that scale, and then they are all trying to do something like, okay, construct a Lego building or of that sense, and then this sort of paradigm would fit in there. And can we get these LLMs to do tasks, something like that? Yeah. So yeah, that's the idea. So I wanted to.
This is an interesting general idea, Surya. I'm curious, what is the, I guess, what is the output space here? Like, are the LLMs just generating text? Are you visualizing that somehow? Maybe second question, to have swarm behavior, you need some exchanging of local information between.
Mhm.
How are you thinking about exchanging information? And I guess, what is a neighborhood in LLM land?
So one example would be like the cellular automata that Meet was also discussing. So each cell, you can conceptually think of them as an LLM, and then you give them a position, and then you tell them that, okay, you can talk to like next 5 neighbors or next 20 neighbors, and then there's and then you try to get them to form a shape, let's say. And question is like, can they form such a shape? And you could scale this idea to kind of like and bridges. Let's say, okay, can these LLMs form a bridge? And then if there are some adverse conditions, and then are they resilient? So in some sense, this is sort of like an advanced level of reasoning, but sort of collective reasoning. Are they able to like communicate between one LLM communicate with the other that are far apart, but like they have to talk between other ones in between? So can they do this sort of like swarm behavior? That's the question. Yeah.
Yeah, this feels more like collaboration task other than swarm behavior. Because I think in swarm behavior, each individual has its own goal. That's not painting something. They want to, I don't know, the birds want to fly somewhere. And then because they communicate locally and they each have the same goal, when they're propagating together, they somehow form this shape and paint a zebra, not the frog, something like that. And then in your case, maybe the goal shouldn't be building a bridge, but I don't know, everyone decides to paint this grid black or white, and the goal is to do something else. But then when you observe,
A practical use case could be like, for example, let's say I want to build a Lego bridge. Let's say I have a bunch of Legos, and there are like 20 such robots, with each one with LLM in it, and then they're trying to together construct this building, let's say.
yeah, I'm just pointing out that the swarm behavior and cellular automata is usually you're trying to do something else, but then some other surprising pattern emerged from the objective.
Okay. Yeah. Okay. Yeah.
A related.
So that's.
Sorry. Go for it.
I think I got disconnected. Sorry, please continue.
I was gonna say a related topic I've seen people research is a little bit different than the swarm framing, a framing where you have many agents acting in an environment, and they're each incentivized to accomplish something particular. And then the cool thing is to see some emergent behavior of the agents, maybe as they're just individually selfish. So one paper that I'm remembering, a visiting student in our lab in grad school, I was in Hod Lipson's lab, and he's definitely interested, and many students were interested in swarm intelligence. This is a visiting student from Japan whose name I kind of forget, sadly. He had a paper where every agent, it lives in a 2D world, it moves around in the 2D world, it can send some, it can send out like a sound, but there's no vision, if I recall. And its only goal is to reproduce. And the way agent reproduces is it like intersects in this large 2D world with another agent, and maybe it waits there for 2 steps or something, and then it can reproduce. Anyway, there was this really cool emergent behavior where agents would, I think there were no sexes, there were no genders. This is all from my hazy memory, but 2 agents would start talking. They couldn't see each other, but they could hear each other, and they would basically agree that one of them will become the like motion in the X dimension agent, and the other one will become the motion in the Y dimension agent, and then they would like stick to their own line, and they would try to meet by just iterating in X and Y. And this was pretty reliable because searching along a one-dimensional manifold is much more efficient than like randomly wandering in 2-dimensional space. They would meet and then they would reproduce, and that behavior emerged as a beneficial behavior. Anyway, I haven't seen anyone do something like that with LLMs, where, for example, the LLMs like emit language and talk to each other and like coordinate. If you tried this, you might see some kind of complicated, almost anthropomorphizable human talking back and forth between agents, like negotiating things, which I think would be super cool to just see in a demo. A little different than the direction you proposed, but
yeah,
same flavor.
yeah. Oh, I see. Okay. Like, let me know the paper. I would love to take a look at if you could find it.
Yeah, I will see if I can find it.
Yeah. So, for example, in these papers, the early works, right? What they were interested was this fix the emergent behavior, and then they ask like, how do I get this emergent behavior? And a lot of like this robotics swarm research, like they are more interested in that. Like, okay, I have seen this emergent behavior in real world in some underwater somewhere, and then how do I get that to that point? And then all the algorithms are about, okay, how do I design an algorithm to get to that emergent behavior? And we could sort of ask the question like, okay, I have this thing that I want to behavior that I want to merge among like 10,000 language models, and then how do I write a prompt that for each individual agent, and then somehow the interaction would emerge that behavior. That's the old question. If they are talking with text, for example, that completely hasn't been explored because it's yeah. So that's all. That's the idea. Yeah.
Thanks for presenting. Really curious to see where it goes. Come back next time and give us an update.
Yeah, sounds good. Yeah.
We can move on to Corbanian.
So this is a somewhat different presentation because it's not about a research project or a research idea, but it's about the Python library that I wrote earlier this year and that I want to do some advertising for. And maybe it's useful for you. So I'm presenting TensorHue, and it was really born out of personal frustration with the way tensors are displayed if you display them in a console. So basically, to show you what I mean, I want to actually write some code. So I have MNIST loaded in my terminal, right? So for example, the 30th image is a pillow image with the label 3. And you can convert that image into a tensor. It's not really tricky, right? Oh, sorry. Yes, of course, the image, not the tuple. And then you get a torch tensor. That is your image. And I have a function that does some image augmentation, right? It maybe rotates the image, adds some noise, converts it into a float tensor called augment. And if I apply that function, I get a different tensor. But I made an error in my function, and something about this tensor is wrong. And my question to you is, can you tell me what is wrong with this tensor? It is a really simple mistake that I made, and it drops So the accuracy of my classifier now drops from, let's say, 99% to only 50%. And it's really hard to tell, right? Because you only see a bunch of numbers. And even those numbers that you see, you don't really see how big they are. Because, well, one might start with a 1 and the other one might start with a 9, but then you've got the scientific notation, and it just makes it really hard to understand what you see. So, of course, as long as you still have a pillow image, you can just show that image, and then a new window pops up and you see the image, right? But once you have tensors, that's not as easy. It's just really difficult. And for example, if you work on a remote machine connected via SSH, you can't even make a new window pop up, right? Because you only connect it via SSH. So I want to first show you what you can do with TensorHue, and then go back into my terminal and show you how it actually can be used. So in general, the idea is that you want to visualize tensors not in some other framework, but directly in your console. And this doesn't just work in the console, but for example, if you have a Jupyter notebook, you can also print in your Jupyter notebook. But the idea is to get a visual impression of the values in your tensor, right? So for example, if you have floating point values, they should be normalized between, in this case, light and dark. And this is like just the Inferno color map for Matplotlib. If you have a Boolean tensor, they could be red and green. And if you have a masked tensor, maybe you want to see which values are actually masked. And those values that are not masked, where are they, right? And TensorHue currently works with NumPy arrays, torch tensors, JAX tensors, and TensorFlow tensors. But it doesn't just work with tensors, it also works with images. Maybe one more thing about the tensor. So for example, one other thing that you really maybe want to visualize in your console is confusion matrices. I know people typically like plot them as like in Matplotlib and then save that as a file, or you just print the numbers and then try to guess which numbers are high and which are low. But it's much easier to see that visualized as a tensor. But what I wanted to show you is this. You can also visualize images, specifically pillow images, in your console with the same command. And maybe it's a bit easier to see that in action. So we have this tensor here, and all we have to do to visualize is it. So first of all, we have to import the method. And you can just install TensorHue with pip install TensorHue, right? So you do this, and then you wrap your tensor in the this command. And now you see what's the problem, right? The problem is that your tensor was transposed. So what you have to do is transpose it again and you get the correct digit. And seeing this visually, I think is much, much, much easier than just looking at the tensor. And for example, since I talked about Booleans, so for example, you could do greater than 0.5. For some, why is this? Okay. Oh, yes, okay, I see. Sorry, maybe let's do this first. So this is the pure image. I have to remove my documentation. Yes. And this, for example, would be the same one as a Boolean, right? So you get these nice color representations of your tensor. And what you can actually do, so for example, some people have like color blindness and they can't differentiate between red and green. Or maybe you also don't like the Inferno color map from Matplotlib. You can also use custom color maps. So maybe to show you the documentation in GitHub, you can create color schemes based on any matplotlib color map, and you can also create your own, and then simply pass that as an argument, and that will override the default colors. So for example, you could say you want black and white as Boolean colors, true and false. One more thing you can do is scale tensors. So for example, I can say scale equals 2, and then the tensor gets rendered larger. This is typically useful for stuff like confusion matrices, right? Where you have tiny tensors that maybe are just 5 by 5 elements big, and you want to display them in a large format, and you can use that. And you can see, for example, in the bottom, we have shape information on the tensor. Something that I want to have in the future is different annotations. For example, in this case, it would be nice to also see the tensor type. Is it an int tensor, Boolean tensor, float tensor, etc.? And yeah, that's pretty much all I have to show. If you want to support TensorHue, you can obviously pip install TensorHue. You can leave a star on GitHub, submit an issue if you find bugs, or if you have a feature that you would like to see implemented. And yes, of course, please use it. And I can also answer questions.
That's really cool. I can't think of how many times I've visualized like a 8x8 tensor in my terminal and it works really well, and then I want to switch to like 200 by 200 and I can't see a thing. This looks really useful.
Yeah. So for example, also if you have a really large image, it auto scales down to the size of your terminal. And you can also determine, like, you can scale down as well, not just up.
Yeah, that's cool.
Do you have any plans for extending it to like language model output distributions? Like
To what? Language model what distributions?
The output distribution. So if you wanted to visualize like the outputs and like tying the positions in the tensor to the like tokens in the vocab.
Oh, but the vocabulary is quite large, right? You've got like,
yeah, you could do like some filtering on it, but it would be pretty cool to like print out like immediately, like, hey, top 5 tokens are these, like really quickly.
Yeah, please submit that as an issue then.
I'm just curious what's powering the image display functionality in terminal.
What is powering it?
Yeah. So what is making
So
terminal?
so what I'm effectively doing is I'm printing Unicode characters that are a small square on top of a colored background. And the library I'm using is Rich. I love Rich. It's a great library.
This reminds me a little bit of the weights and biases, like loss plots in the console. You know, like they added that at some point. Like, yeah, you should go on the web and see the whole web version. But there's also like this cute little line diagram of like, oh, your loss is going down, how many steps it's been, or whatever. The learning rate decay, and you can debug basic problems just in the console.
Yeah, that could be something you add, plotting 1D tensor as like a line plot.
Mm-hmm.
That would be
sorry.
That would be so awesome to like be able to like easily recreate those like little matplotlib like graphs as your sanity check, because like your SSH into like a server, you're not gonna like save the matplotlib file and do all that stuff.
I have to look at how weights and biases does that. I haven't seen these plots because I haven't used it in a while. But that would be interesting. I know there are a couple of libraries that try to do some plotting, like for example, histograms or bar charts. And that works reasonably well because you only have blocks, like Unicode blocks that you have to stack on top of each other's. But lines are a bit tricky because there's just not many characters that you can use.
You wouldn't have access to the full color space, but if you want to 4x the resolution, you could use some of those boxes that have like 4 sections shown there, or even higher. I think this is maybe what WMB does. You can use the Braille characters, which have up to what, 8 8 dots, I think, each. So you wouldn't be able to change the color every single one, but you could show like a bit higher res, maybe for the binary masks, for example.
Hmm. Yeah, that's it. Spread the word.
Another feature request, I suppose, whenever I end up trying to visualize a pandas data frame, it's the same fundamental problem. You can see, you know, up to 8 columns and up to 10 or 20 lines on one screen. As soon as it gets beyond that, I don't know, you might have 10 a pandas data frame with 10,000 rows, and you're looking at like the first 5 entries, but you don't know whether like your data is missing for the first 200 and then your data appears or something, which happens all the time. You have edge effects having to do with the beginning of a data set or the end, right? I've often wanted the same thing, like df, push enter, and rather than the 8 columns with the next 100 columns truncated and 10 rows with the middle 2000 rows truncated, you see like a holistic interpretation of the whole thing somehow.
Yeah, so this is really doing two purposes, this tool. First, converting numbers into just visual hues, as you name it, and seeing it holistically, seeing the whole thing, no matter how big the dimensions are. Do you have a way to handle like missing data or like nans in the middle of a tensor?
Yeah, so there in this color scheme, there's many different color variables that you can define. Also, for example, for plus infinity and negative infinity, and for none. So you could, for example, define a different color for each of these. It's just like at some point they become too colorful if you have a lot of these values, and it shouldn't be in the range of 0 to 1 because every tensor gets normalized between 0 and 1. Except if you specify you want it between -1 and 1, then you can have like a center that you define, and you've got diverging color maps, just like in matplotlib, for example, cool warm. But for these special cases, you can define colors, yeah.
Any thoughts on, you know, 4-dimensional tensors and how to show?
Yeah, that's currently the biggest limitation. So it can, at the moment, only display 2D tensors. I guess it would be super easy for 3D tensors to say, okay, just slice the first 2 and the last 2 elements and then print those. And higher dimensions, to be honest, I have no idea how to implement that. It's even if you just look at regular PyTorch tensors with these ellipses in between, it becomes really messy.
Yeah.
And then you have these brackets to make clear what is part of what. And I try to avoid these brackets surrounding the plots. Yeah. I'm open for suggestions though.
I think fundamentally your limit is like, what is the bandwidth that you can get from the terminal into the human brain, right? And you've increased that quite a lot with this library, right? The pixels you show are much more than, you transmit a lot more information to the human brain than the scientific notation, right? Which we find difficult to interpret. If you can add somehow motion or animation, that can also really 10x the bandwidth, I think. I don't know if it's possible with, you know, ncurses or something where you're like, for example, you have a 4-dimensional tensor and you show it, and if the user pushes something or scrolls, you can like quickly slice through it forward and back and see different slices. You could also allow different aggregations. For example, like show me this data as if it was a block and I was seeing the first layer. Okay, now show me as if I had X-ray and my vision was averaging all the values through it. Something like that. Or like show me a few layers worth, but not all the layers. All right, thanks, Corbinian. Should move on to the last one.
Yeah, let's move on to Tahoe. Have a different background now.
Let me just like share the screen right quick. So I prepared just like a small presentation of 33 slides. I will try to go through it really fast. I will share with you the link, everyone.
There's 3 seconds per slide.
Let me share the link. So this is like a project that I started late in July. think after one of the town hall meetings that we had in that time, I was like just trying to kind of discover some kind of notions that are beyond the Euclidean like kind of metrics, like the Euclidean space. And while I was trying to kind of like play around with things, I actually just like created a cool thing, even though it was rejected by ICLR, but it was a cool thing. This is a cool thing. It's not rejected, it's just like was 2 out of 10, like in this year. So I'm Taha, just me. So the main contribution of this this work is creating 2 new similarity matrices, the YATS and the Cosiyat, which is just like the inverse of the other one. And the other thing was like creating a new contrastive learning, a supervised contrastive learning framework. And the last thing was like the a loss functions that is kind of compatible with this framework, with the CL framework, called anchor-free contrastive learning, which actually removes the anchor from the like the notion of anchor from actually the pre-training, and it tries to rely on just like the batch composition, or how to kind of create the batch, and then how to feed that batch to the model. So I will try to go through all of these. Hopefully I will have enough time by the end of 15 minutes. So like just quick recap, like just like the contrastive learning is just, or the supervised contrastive learning. So basically you have like an anchor point, and then you have an anchor image and a positive image, which is like similar to the anchor image. And then you have a negative image, which is an image coming from like a different kind of a different class, or just like something different. And basically in contrastive learning or supervised contrastive learning, the main goal is to actually make the embedings of the images coming from similar classes kind of get close to each other. And the other images, or like the anchor with the image coming from the different class, they should kind of get away from each other. But the main kind of metric that is used for this task is like either the cosine similarity or the Euclidean distance, and also there is like the same like a softmax loss, which is like the that is used by ANFO-NC. But each one of them is like is kind of working in a different like metric space or semi-metric space, and some of them are not even metric spaces. So the Euclidean distance is the only metric space in the that is like that is a metric space. The cosine and also like the dot products, the cosine similarity and the dot products and the ANFO-NC, they are different like metrics. And also like there is like some methods that use the max function, which is not good because it's like it introduced the non-continuity into the loss landscape, which creates like a lot of problems. Just like a lot of problems. There is other methods. There is like some lifted structure methods that actually try to create like a combination of like pairs and like multiple negatives. Which is exactly what they did in the n-pair loss and lifted structure loss, where they will just like they will take an image, they will try to add like in the same row, they will add another like image that is positive, and then for the rest of the images, they will be all of them are negative, and then they will try to like do a softmax of which one of them is the the output of the dot products between the x and positive should be always 1, and the rest should be 0. And we all just like discuss the negative from the contrastive learning, and only try to kind of learn the or minimize the distance between similar images. Same thing for same Cellular. And then there is clip, which is also like one of the other methods that actually remove the anchor from the contrastive learning. But what it does is tries to kind of like make the images or the image and the image text token pair that are similar, kind of provide you softmax on the value 1, and then for the rest of them, the softmax should like the values that they here should be all 0. but it's limited to just like pairs of modalities or just like pairs of similar inputs. So the idea that I had like was, why not kind of remove the anchor from everything, and instead of just like comparing two images or two like inputs from the same class, why don't we compare them all at all, like one image with all the other classes all at the same kind of operation. But the main like the main limitation that I found, like there is no defined loss function for this specific task. And the other thing was like that's why kind of like I try to kind of like look in topology and other stuff, like how can I find or how can I minimize a similarity matrix to actually make the different impedance away from each other, all of them at once. Just like all of them are different, and they need to get away from each other, while the images coming from the same from the same class, they should all kind of get close to each other. And that's kind of like where I created my like this school, which is called anchor-free contrastive learning. And so the first phase of this anchor-free contrastive learning, you will try to sample 4 different classes. For example, I'm making an example from CFAR. So I took the cats, dogs, and deer and frog, and I just like took from each kind of like class. I will take n images. For this example, I'm just taking 5 images from each of those like sampled classes, and then I feed that batch to actually my ResNet, and I generate the impedance using that ResNet, and then I reorder those like impedance into into this shape, where I have like for each row in this like mini batches, each row is like all images coming or all impedance coming from the same class, just like for example these 4 classes. And then I will calculate the similar or the loss that actually tries to minimize the similarity, or to try to minimize, try to kind of reduce the distance between, or the similarity between the images or the impedance coming from the same class, and using this like the LSIM CLS for similar classes. And then I calculate for each row, I calculate this loss here to generate, or to kind of generate the final like a loss, similar loss for my batch. And then I will take like the I will calculate the loss not row wise, but kind of like column wise, where each like embedding is different from the other classes here. And I calculated using the I think I forgot here. Anyway, I think I have it here, but it's all right. So I will explain the loss later. So I calculate this sim for this specific kind of like mini batch, and then I calculate the same thing for all the batches that I have here, like for all the columns that I have, the mini batches that I have. I calculate the loss or the similar loss for all of them. And then I will just like sum it up. And then I do something else, which is like I will try to calculate the mean of each row here. And I have like the center of this like distribution for each class here. And then I will try to kind of like make the center kind of away from each other, like as far as they can from each other. And then I will do this final sum, which is just like the sum of all those like 3 losses that I calculate, the LSIM, this one, and L dissimilar, and then the L mean, or mean like the mean dissim, which is kind of trying also to kind of differentiate between the means of each class. And that's like the final loss that I will do the back propagation with. And it can be like, you can generate it just like you can take or sample as many classes as you want, and as many images as you want from your kind of data sets. As like if your data set is large, or you have more images in each class, you can just like make this n here as big as you can. And also if you have more classes, you can generate it as you want.
So is there,
yes, sorry.
do you have an intuition for why you think this will work better than competing approaches?
So when you like, for example, if we take the cosine similarity to actually like make the impedance from dissimilar classes push away from each other, you don't specify where they push. You will just like, let's take sample 2 like images, and then they will just like push randomly. And then if you have like another image from other class tries to actually just like push them away, they will again push away. So it will be hard. It will make it a bit hard for them to actually know where or which direction to choose to push away from each other. They will just like kind of repel from each other like this. And then if we have another class like here from another embedded from here, they will repel like this, and without actually any direction. So when you have a batch that contains all the, or most of the classes, for example, I have 4 classes, you will tell them, just like try to kind of figure out where to push. So they will try to actually, this is exactly this slide here. So for 3 classes, I make them push away orthogonally instead of like pushing them away like linearly. I will try to force them to be orthogonal with each other. So most of the kind of like the losses, they will try to actually just like push away, either like they have a linear dependency between them. But for my loss, it's orthogonal and it's non-linear.
Okay.
And that's kind of like the loss that I propose, and also like the new similarity matrix that I propose, which is like the yachts. This is the yachts, and this is the posiyat that I will talk about later. But the main idea is just like images from similar classes. They should not be they should not be orthogonal. They should be parallel. If you remember, like like when you calculate the cosine similarity between 2 vectors, it will tell you either your vector is -1, which is dissimilar, or 1, which is similar. It will just like tell you the linear dependency between them. But there is actually a missing information in the middle that nobody uses in the literature, which is like the orthogonality, which is like when you have 2 vectors that are orthogonal, the cosine similarity, the dot product, they are all like equal to 0. And I did not find like anyone that is like using it in the literature. So I just like try to kind of like test it out, which is exactly what I did. So the O in this equation here, the OIE is like calculating the dot product square. The square of the dot product will always give you the minimal value is 0, and 1 or infinity for like the kind of, for if they are parallel. If 2 vectors are parallel, it will give you like infinity. And if the 2 vectors are orthogonal, it will give you 0, because I did the square. Before it was just like between -infinity and infinity, and when you square that, it gave me like the minimal value, which is 0, and plus infinity. And then there is like the other like part of it, which is the distance, which is just like the Euclidean distance squared. And then I have like an epsilon here, just like a small epsilon. This epsilon solved a lot of trouble for me. And like both like mathematical and also like from experiments, it just like provides you with a like to kind of like protect you from the kind of when 2 values are orthogonal, are perfectly orthogonal, the dot product between them will be 0. So it will kind of, for the first term, it will kind of like lead to an infinity, or like it will lead to an undefined. And then for the second term, when we have like a 2 impedance that collapse together, it will give you 0, which is also like we should get rid of it. So I just like added that epsilon. And then these are the 2 products that I have, like the new similarity matrix that I had. So I had hard time actually proving this. So for the paper that I submitted to ICLR, I was under the impression that they were both symmetric, but it was until I think 3 days ago that I kind of like proved that the first term, the yacht product, or the like the E without any like overline above it, the first term here is actually a pseudometric space. which means it respects all the the properties of a metric space besides the second one, which is like the distance or the similarity, the metric between two impedance space is equal to 0, implies that the two impedance are like both of them are equal to each other. The first product is not is not defined when it comes like to that to when two impedance are equal to each other, because like it will introduce 0 into the equation, and it will kind of lead to like undefined. So I just like it was pseudometric instead of metric. And the second one is actually also pseudometric. I just like proved it while I was in the airplane. So while I was in the airplane today, I finished the presentation for today, and I proved the anyway. So like the second one is pseudometric, and if I added like the epsilon to the bottom, it becomes metric. And yes, so the SimO, the first like the first product here, the one at the top, it will when you minimize it, it will make like the second one, the posite, this one and here. It will make the distance between the two impedance like close to 0, with the dot products like going to infinity, because these two impedance will kind of be parallel to each other. They would be parallel to each other. And then for the dissimilar classes, using the first product, will be orthogonal with each other in the impedance space. So this is like exactly the one that I mentioned earlier. When you are calculating the dot product between two vectors, this is called similar, which will give you a plus infinity value, and then this is like opposite, which gives you minus infinity, and then there is this information that nobody is using. So that's what I ended up using here.
We're a bit over time. We should try to wrap up.
Right. So like I think I faced like some numerical instabilities here. The yacht product is really kind of sensitive to magnitude. Also like magnitude on also like orthogonality. So it gives me like some values with 10 to the power of 7. So I solved it with 1 plus magnitude, log of 1 plus the score or the similarity score. And you can see like the dot product is just gives you is not like a good metric to actually use for orthogonality alone. Same thing for the cosine similarity, and same thing for the Euclidean distance. And the thing that I found out like after submitting again is my product is kind of similar to the inverse square law, the one that is like Kepler created, and also like Newton, the first law of Newton, gravity of Newton, and also like the Coulomb's law, and also the Gauss law. Kind of they are all of them are similar in a way. And for the accuracy, like I had like some like the numerical instability that during the pre-training was like a problem for me until this like morning, and I solved it like barely. So it was like it's gave me like it needed the pre-training of this model needed I think around 1 million iteration in the results that I published that I submitted in ICLR paper. And the thing is like the PCA provided like kind of insight that all the impedance learned by the model are orthogonal with each other, and like intra-orthogonality between the different classes. So each column here and like represents a class, and each row represents like the pair classes, like the pair PCA between the different classes. And the bottom one represents like the lower triangle represents the TensorHue of those impedance. And it's also like I also kind of like saw that there is like a cool thing that is happening here. So the model, as it progresses in the training, it learns one class at a time instead of like learning everything at once. But the main problem remained was like the instability of the loss function, which kind of like shot high because like the yacht product is really sensitive. And then like the things from the things like I needed to improve here, I needed like to compare the model on different data sets, but due to the instability, I couldn't kind of like finish that in time. And also like include other data sets and include like how much the training sets that differentiate between like when you kind of sample from a smaller data set, how kind of the fine tuning will be impacted of these models. And some bottlenecks that I had, like I think time compute. So at the beginning of this project, I was just trying to scrap compute from different places, from Kaggle Collab, and then I got like a few $100 from the GDE program, which really kind of helps in creating the script and everything. And there was like a problem with the similarity, so I was able to fix it, like kind of. So the fix that I did like this morning actually was to use this kind of notation here. So just like 1 plus d over dg, and I was able to actually reduce the pre-training from 600 iterations to just like 5K iteration, just like on CFAR10. And this like everything was kind of like separate. The magnitude or the magnitude of this score is like 10 to the power 7, but when I used the log, I reduced it to 20. So when I did the calculation of the loss using this one this morning, it was really helpful. And I was really stressed with the presentation, so I had to kind of solve it before the presentation. I gave myself the deadline. Luckily, I was able to solve it. And so like this is a comparison between the different properties. I think this is like a metric space, pseudo-metric space, like some definitions. And the other thing, I'm not sure. So the other thing that I did during this past month was a bit like tricky. So I used this the yacht products instead of the dot product in the neuron, and I removed in the artificial neuron. I used this product instead of the dot product between the weights and the inputs. It's like x dot w plus b. I removed that and I did my product, and it actually showed some interesting stuff. I'm not sure. Can I? Do I have more time?
We're at 23 minutes, so we're way over.
Okay.
Maybe we should wrap up.
Sorry.
And then if
All right.
anyone can
That's
stick around
it.
past the end of the meeting, we can keep talking if people want.
All right. So that's it. Thank you very much. If you have any questions, feel free to ask. It was a
lot of information quickly. Maybe one question from anyone?
I checked out your paper. I think, of course, I don't know. I didn't see the reviews, but I think maybe they will be complaining about no comparison to existing.
Yes.
methods.
Yes.
Yeah.
So that's kind of like I tried to. So the main problem that I couldn't add more comparisons was because of the instability. The instability, just like when I calculate the yacht product between two kind of like vectors, it's really sensitive to kind of how close they are. If they get close, it really shoots up to infinity. And it really kind of like shoots to infinity. This is what I showed in this slide here. So this is like in this in the one at the bottom here. The magnitude of like when I calculate the score between two vectors that are like where the theta between them is like close to each other, the magnitude just like shoots up really kind of to infinity. Just like this one, it's just like a magnitude a vector with a magnitude of 10. When I did two vectors of magnitude of 10 that are kind of close to each other, the yacht product is going to infinity. So I was only able to actually solve this by doing the kind of similar to a soft log or something like that, by just like a soft plus, I think, by just doing the log 1 plus this kind of yacht product, I was able to actually just like reduce that magnitude so it's less sensitive. When I pre-train it, the pre-training is still going right now. And when I pre-trained it this morning, I received like, I only needed 5,000 iterations to actually get 85. When I pre-trained the model on the fine-tuning, just one epoch, I got 80% on CFAR10. And I think I will run more experiments now with this new loss function. And it's a whole different loss, but I will try to actually just like figure out like how to, and also how I couldn't write the paper in a good way. I'm not proud of it. It was like a bit kind of, that's kind of one of the reviews just like said, it's just like a bunch of things kind of put together. But I think it's true. I will try to kind of like write it differently, especially since I used the same thing for another paper that I'm submitting to CVPR. Hopefully it will get rejected too, but it will hopefully just like I will try to finish it.
Yeah, I think adding some baseline comparisons would be pretty useful. And a lot of papers or a lot of research projects before they're done just look like a collection of random experiments, and you really have to wait until you see the beautiful holistic kind of picture emerge, and then telling that story hopefully will be simpler and more clear and everything. We should wrap up now because we're pretty far over time. Let's maybe thank all the speakers. There were 4 great talks. Thanks all of you.
Thanks for having me.
Yeah, thanks for this was amazing. Yeah,
looking forward to hearing kind of follow-up presentations from everyone actually.
Yeah. Okay. Thanks for spending your morning/afternoon/evening with us. Okay. See you next time.